This is Team F, conformed by Elizabeth Alvarado, Alexandra Lizárraga, and Valentina Avendaño, and we're gonna be talking about vibration, which is the topic 3. Simple harmonic motion. This motion is a kind of oscillation that repeats over time, and it's called periodic motion. An example could be a child in a swing. 3 important factors of this motion are that the movement is periodic, and there's absence of friction, and it's produced by a restitution force, which is a force that will make the object go back to the original position. In this motion, any object oscillates around an equilibrium position, and once the object goes away from its central position, it reaches the same maximum distance sideways. More examples of this could be springs, pendulums, and circular motions. These type of vibrations could be also studied as waves. Now we're going to talk about some important definitions, starting with amplitude, which is measured in meters, and it's represented with the letter A, and is the maximum displacement from the equilibrium position. Period is measured in seconds, represented by the letter T, and it's the time where something goes back to its original position. Is represented by the letter F, and its units are hertz. It can be defined as the number of cycles in only 1 second. Here we can see some formulas that show us the relation between period and frequency. Angular displacement. This is represented by the letter theta, and it's the number of oscillations, and it's expressed in radians. And lastly, angular frequency, which is represented by the letter omega, and its units are radians over seconds. This is the number of cycles per second. And here's some formulas that show us also the relation between angular frequency, and angular displacement and angular frequency. Simple harmonic motion and Hooke's law. In this example or picture, we can see how if we stretch a spring, a force will make the spring to go back and forth to its resting position. But if there's no friction, the spring will be going back and forth, but with the same amplitude on both sides. And here we can see the formula that is used for Hooke's law, and if we pay attention, we can see how there's a minus sign in the spring constant, and that's because when we pull the string, making it go back, it moves towards to a positive side.
The simple harmonic motion and the second Newton's law. When we want to know the acceleration in which the mass is attached to a spring oscillates, we can use the Newton's second law because, we know how it works. So it has a formula that is A equals minus K multiplied by X over M. That it's, in simple terms, if we divide the restoring force by the mass, we will get the acceleration. So in the formula, A means acceleration, Kx is the force, and M is the mass. The units of this equation are meter per second. Energy in simple harmonic motion. The potential energy can be calculated by the following formula. U equals to 1/2 of Kx elevated to the square. These the potential energy units are joules. So we can also have a conservation of energy equation because there is no friction in the oscillator. The formula, the equation is 1/2 of Kx elevated to the square plus 1/2 of mv elevated to the square is equal to 1/2 of K x1 elevated to the square plus 1/2 of mv elevated to the square. And this is the equation, and it can change depending on what is the problem asking you. You may cancel some values to make it simpler and to make it, correct.
Motion equations. The vibration of the simple harmonic motion can be studied as waves because we have an amplitude of motion, a period, and a frequency of oscillation. This phenomenon can be approached by comparing it with a sinusoidal wave. The period t and frequency f of a simple harmonic oscillator are independent of amplitude. The string of a guitar, for example, oscillates with the same frequency whether plucked gently or hard. Position as function of time. If simple harmonic motion is related to a sinusoidal wave, then the position x at any given time can be found by the next equation. The position x will be given in meters and the time in seconds. The equation for the position as function of time is good for modeling data, where the position of the block at the initial time equals to 0 seconds is at the amplitude a and the initial velocity is 0. Velocity as function of time. When a restoring force acts on the oscillator, the velocity at the amplitude is going to be 0 and the maximum velocity will be at the equilibrium position. Thus, the equation to find velocity at any given time will be the following equation. The maximum velocity for the spring is given by the next equation. The maximum velocity occurs at the equilibrium position when x is equal to 0. When the mass is moving toward x equals plus a, the maximum velocity in the negative direction is attained at the equilibrium position. Acceleration as function of time. The acceleration of the simple harmonic motion at any time will be given by the next equation. The SI unit for acceleration is meters over seconds squared.
Wave phenomena. We can express oscillator in terms of its frequency and period. For frequency, the formula is f equals to 1 over 2 pi multiplied by a square root of minus a over x. F meaning the frequency, a meaning acceleration, and x meaning position. This formula, its units are represented in hertz, and for the other side, the formula of period is t equals to 2 pi multiplied by a square root of minus x over a. T meaning the period, x meaning position, and a acceleration. This formula is represented on seconds. Using the previous oscillator equations, we can apply them for the spring mass assembled. For frequency, the formula will be f equals to 1 over 2 pi multiplied by the square root of k over m. F meaning frequency, k the spring constant, and m the mass. And for period, the formula will be t equals 2 pi multiplied by m over k. As well, m meaning mass, k meaning the spring constant, and t meaning period. In real life, we can apply these formulas. For example, in a simple pendulum, if you want to calculate how much is its oscillation frequency and the oscillation period, that will be a good example to apply it in real life.
Example of the simple harmonic motion. A mass of 3 kilograms attached to a spring constant K, 120 newtons over meters, is pulled with a force of 96 newtons and then released. If it comes back to its initial position in 7 seconds, calculate the following. The moving period, which is given in the problem, is time equals 7 seconds. The movement frequency, the angular frequency, the displacement amplitude, the displacement after 9 seconds, the maximum velocity, the speed after 9 seconds, and the acceleration after 9 seconds. We can all calculate this with the formulas given in the explanation.